Welcome everybody. Today, in the next bit less than 2 hours, we are going to share with all of you the work done so far by 4 Horizon Europe projects that are 4 sister projects, because the 4 of them were funded within the same topic. This is the second webinar organized in the HARTU project with the support of partners or with the support of sister projects. The first one, I think, is available on the HARTU repository. The registrations and the documents presenting during the first webinar are available in HARTU's website and LinkedIn page. That was run a bit less than a year ago, and it was dedicated to soft robots, to the design and implementation of soft handles, soft gripping for robotic arms, and it was run by the Polytechnic of Bari, which is one of the partners of the HARTU project. Today and this year, we decided to dedicate the second webinar to one aspect of that the 4 projects have in common, but a lot of other European funded and co-funded projects have in common. That is the social sciences and humanities. So how aspects related to the role of humans within manufacturing context and projects, how can be designed, assessed, and how can be monitored in terms of impact on their well-being, but also impact on their acceptance issues, but also impact on ethic aspects, but also impact on how this will in a way change the profiles of workers, so the profile of the workforce, and possibly which new skills and competencies will be needed for operating in innovative production context. The 4 projects so today are going to quickly in a way, because 20 minutes is quite quickly probably for the work done during 2 and more years of the projects, of the 3 projects, and for the, let's say, the last 10 months, the last remaining 10 months. So it's a let's say quick overview of what each of the 4 projects are doing in terms of social sciences and humanities, but we thought that this could be an interesting topic for first of all, for us to share our, let's say, best practices, for us to share our methodologies and assumptions in doing this work in the 4 projects, but also for possible, let's say, external participants to this webinar to know a bit more the way we interpreted social sciences and humanities to be able to contribute to research and development projects into the manufacturing and engineering areas. So today I'll try to quickly share the agenda. So just let me okay. So this is the hopefully the final version of the agenda. Marta, correct me if I am wrong.
Yes.
Okay. So we are going to have the, let's say, the SMARTHANDLE, Agile Hand, Masterly, and HARTU projects to present during 20 minutes the work done in social sciences and humanities. Each of the presentations will be introduced by a very, let's say, short introduction done by Marta. And then at the end of the 4 presentations, we can have some wrap up and some take also some questions, I guess, Marta, from the participants for let's say quick answers or for more let's say long follow up in case some answers require more time. So yeah, basically the presenters today will be Arantxa from Technalia, coordinating the SMARTHANDLE project. Then she will hand over to Hazam from the Interop V Lab from the Agile End project. Then third will be Sarah from University of Cranfield for the Masterly project, and then Giovanni will close from Deep Blue will close the presentations for the HARTU project. I think I don't know if there are any questions or if there is anything else to add here. Otherwise, I can leave the floor to Marta for introducing Arantxa. That's the first presenter. Marta, don't worry, we will be keeping up admitting people.
Thank you. Thank you.
Okay, thanks.
Thank you, Linda, for this warm welcome, and thank you all for being here. And also thank you to our speakers for being with us today. The first project of today will be SMARTHANDLE, as Linda said. SMARTHANDLE is a project aims to enhance both manual and automated production lines, allowing them to produce a wider variety of products with fewer resources. Their key challenges are product variability, limited autonomous decision-making, and the need for adaptable control and efficient planning system. So the project to address these challenges is developing technologies that improve dexterity, reconfiguration, and autonomous reasoning. So, and also this innovation will be tested in real-world manufacturing scenarios, in this case in metal industry, consumer goods, and automated supply. With us today to present the project, we have Dr. Arantxa Renteira, project manager at Technicalia Health Division, with an extensive expertise in robotics, automation, and human-machine interfaces. So she will be discussing with us about the ethical and social consideration of integrating collaborative robotics into manufacturing. Dr. Renteira, the floor is yours. You can share your screen if you want. Oh, no.
Thank you, Marta.
Yes.
Thank you, Marta. Thank you, Linda. I will share my screen. That one. Share. Okay. Can you see my screen?
Yes.
Yeah. Okay. I will put in presentation mode.
Okay.
So my talk will be regarding the ethical and social issues when we try to enter or to integrate a collaborative robot in a manufacturing or production line. I belong to Technalia Research Center in Spain, and together with other members of the consortium, we work in a SMARTHANDLE project, which will finish this year in December with the pilots and validation task regarding how we are going to integrate robots and humans in the production line. The problem that we have identified within the SMARTHANDLE is the manufacturing industry in Europe, which is representing 33 million jobs in the region, with high level of growth, or 60% of productivity growth in the coming year. And the problem that is that the people and market are demanding more and more different products with shorter life cycles. So this implies a problem of how to reconfigure the production lines and how to change rapidly the machines, the robot, the automated means of production in order to offer those quickly changing products to the market. The aim is obviously to produce more and more differently with less means less production means and short changing times in the production lines. The objectives of the Smart Handle project, you can see here, is obviously to focus on the more automation and intelligent development of new production lines, in integrating also collaborative robots, software based on artificial intelligence, and higher degree of parameterization of all the production means. But also we are trying to put the focus on how the workers will accept the presence of collaborative robots together with the workers in the manufacturing lines. And that's why we have a complete work package dedicated not only to the definition of requirements, but also to the definition and creation of design guidelines in order to have the human worker in the center of the design of the whole manufacturing. Sorry?
I think
Yeah.
I think your presentation is not shared.
Yeah, I was.
Okay. I will stop
Yeah, the
sharing.
slides are not. Yeah, the slides were not changing. Yes.
Oh, okay. Sorry.
No, don't worry.
I will stop sharing and share again, maybe.
Yes, yes, you already stopped sharing.
Yeah. I'm going to share.
Maybe it is the second screen, I think.
Okay.
Can you see now? Maybe it's not the presentation.
It's
No?
not full mode, but I guess it is the second screen.
Yeah, I want change to full mode and keep like this. Maybe it's better. So you can see now the slide with the objectives of the
Yes.
project.
Mhm.
Okay. I was mentioning that apart from all the research and development within the project on the technological part, artificial intelligence, reconfiguration means, high-level software, we are going also to focus on the definition of guidelines in order to have the worker in the center of the manufacturing lines. So the idea is to develop intelligent and reconfigurable agents within the project, both software and hardware agents, smart handling tools, and high-level accessorization and monetization of the lines. But as you can see, we will have also people working together with robots in all the cases that we are going to validate, both on the steel manufacturing, the pilots regarding consumer goods handling, and also the disassembly of car batteries. We will have people working together with collaborative robots, and this implies a lot of problems of acceptance, of safety, and everything. Why? Because we have the problem that a person and a robot must collaborate in a way that the people or the worker has enough rely on how the robot behaves when the robot is moving around the people. There is a complex communication and feedback loops between the worker and the robot that must be clear enough for the worker to trust that and to be safe enough with when he's working and moving around a collaborative robot. And what we can see is that now with the integration also of artificial intelligence within the robotic, we have more and more risk for the operator that maybe he doesn't or she doesn't know how the robot will respond to a specific posture of the body or posture of or the hands of the worker, are trying to see what will be the next step that the robot will take, depending on the position of the worker or the gesture that he does with his hands, his arms, or whatever kind of communication between the two, the robot and the worker. Here we can see some statistics that we obtained in a past European project that we did regarding the analysis of collaboration between workers and collaborative robots or interfaces between people and robots. And we were performing some surveys, and we obtained some information from a lot of people from different fields of industry. You can see here how they feel of the presence of robots in the manufacturing lines, or in general in jobs in Europe. They think that the robots won't steal the jobs, but that the robots will be necessary, but they also will need some kind of careful management. So they don't trust 100% on the robotics part. If you see this statistic, this shows that people are accepting robots as far as they are in a well-limited working place. If the robot is in a manufacturing site, okay, they will accept, because usually the robot used to be in a very limited space with fences and a lot of safety measures in order to avoid any accident between robot and human. But if you see how they accept the presence of robots in another kind of environments, like education, caring of elderly, or medical areas, the level of comfortability is decreasing. So we have to pay attention to this kind of issues when we are talking about how to integrate robots and people. About 75% of people think that the privacy data and the personal data could be in a risky way in the future regarding the use of robots and artificial intelligence in the everyday life, and also in the working life or working environment, where more and more a lot of data are being used. Some statistics also shows that the people usually disagree when they are asked about the importance of who could be the first thing to take into account. On one side, the economics and productivity of the manufacturing line with a robot, or the ethical and social issues when trying to integrate that robot. They think that the ethical and social issues should be also taken into account when trying to put a robot in the working place. Also, that from their point of view, they agree that up to now too little attention is being paid to the needs of the workers when a manufacturing workplace is designed. The company usually defines all the manufacturing lines, all the tasks, all the machinery, thinking about the productivity, the cycle time, how many robots, how many machines, what is the best layout for the robots, for the machinery to produce more produce in less times, and few times the comfortability or the well-being of the worker is taken into account. So the thing is that we should think about how the person behaves when he or she is working together with a collaborative robot. When there is a place where the arms, the hand, the body of the person is the same area where the robot also moves in a certain speed. It's true that the collaborative robot usually moves a bit slower, and when the robot is approaching to the human, the robot slows down. But on the other hand, the company wants a robot to perform rapidly the task in order to be proficient enough. So we have here a balance between how the robot is behaving and trying to produce the products and doing the tasks, and how the human worker has to behave in order to feel safe, to feel comfortable, but also to feel that he has the control or the decision about the task over the robot. So this is a balance not only on the physical part of the collaboration between human and robot, but also on the psychological part of the collaboration between human and machine. Here we have a lot of interaction, how the robot with a lot of sensors may interpret the movement of the worker and just the opposite, how the worker interprets the movement of a robot, how the robot approaches to a certain point when where the user is also doing some kind of task. So we must design a common protocol which is convenient both for the human and for the robot in order to make the things be produced, but also in order to make the worker feel safe and confident enough. So we can think about how we can translate the ethical principles that were applied in the past to the human and the normal life of humans to the now increasing use of collaborative robots in manufacturing lines or in everyday life, not only manufacturing, but robots in other fields of production. And we can define those 7 principles that are recognized by experts in ethical and moral principles. Just a quick review that talking about human dignity, that is respecting human dignity and integrity, the creation of robot designs aim at protecting the workers' vulnerability and the growth of the workers' capacities. The second one, protecting vulnerable individuals that they are able to contribute to the development of the autonomy. The third one is, of course, the value of privacy and confidentiality of personal data. The fourth is the robotic designs must be subjected to a testing to guarantee the security and physical safety of the worker, but also the integrity of the worker. The fifth is the principle that means that potential harm must be minimized and the benefit must be maximized, improving the quality of life. The sixth is sharing the benefits when we take into account some populations that could be in a disadvantageous position. For example, elderly workers, women that are now entering in the production and manual handling and manual operation. Maybe they need to be treated in a different way when we try to enter a robot to collaborate with a specific kind of population. And the last one is respecting and protecting the environment and future generation in order to avoid the robotic divide or robotic gap. That every people should be able enough to work within a robot independently of the background of the people. We have worked also on the so-called responsible research and innovation, trying to develop engaging technologies and not alienating technologies. So we should think about how to define and construct and to integrate a robot into a production line, following those 5, let's say, parameters or objectives. No? Trying to get a robot that is open to every kind of manufacturing requirements, versatility, docility, that is that the people doesn't feel threatened by the robot, and also thinking about how the robot will be repaired, updated, and maintained, and or together with the needs of the company, and of course that the worker is able to understand the behavior of the robot with easy to understand instruction and a comprehensive design of the operation that the robot is taking. In the case of Smart Handle and focus on the analysis of how to integrate the human worker within the manufacturing lines that we are developing within the project, we have designed the so-called design guidelines, human-centered design guidelines. We have developed about 25 or more guidelines that are more or less classified as these three groups, taking into account the human characteristic, the task characteristic, and the robot characteristic. And the thing is that the manufacturing line should be defined taking into account the task in such a way that the humans' cognitive and physical abilities are well utilized and well used, and the human worker should perceive the contributions and be sure that he has the control over the work of the robot. So he feels or she feels that he's valuable and impactful. And also a well balance between the responsibilities of the human and the work and the robot should be stated. So the human feels that he supports the robot, but when he needs someone from the robot is able to react in time and to be in a well balance between the tasks that are performed by the robot and the worker. The thing is that the robot should provide also enough feedback to the human to be sure that the collaboration is in time and with exact information that are required. That's why the robots should have enough sensors and means of sending the useful information to the worker, and just in the opposite side. And also that the human worker should have enough autonomy to take the exact decision when the robot needs, and also to control the execution of the whole task in the manufacturing and the decision making. So the balance between the robot and the worker should be the right one in order to have the worker happy and with the feeling that he's safe and that he has the control over the robot. Just to finish, there are some groups working on ethical and social issues at European level, and some standards that you can see on the slide. And we see that more and more different bodies and agencies are working on that part of the technology development when dealing with interactive robots. Because not only in the manufacturing area, but also in other areas when robots try to be used, there are more and more problems regarding the acceptance and the social acceptance of interactive robotics by the people, not workers, but maybe normal people in their everyday life. So this is all from my side. Thank you for your attention, and I keep at your disposal for any answers at the end of the webinar.
Thank you, Dr. Integra. It was very interesting. Yes, as she said, if you already have some question, you can start typing them in the chat so we can collect them. At the end of the webinar, we can address them all together. And now we can move forward to the next project. We have the project Agile Hand, a project focused on improving the grading, handling, and packing of soft and deformable products. They are addressing key challenges such as the accurate and cost-effective quality assessment for delicate goods, the efficient robotic handling of diverse products and objectives, and AI-driven adaptive control for synchronized production and logistic flows. The project is being tested in 4 real-world applications. They are working with sorting and packing of vegetables, grading and handling of berries, handling slippery goods like fish, and batching and packing soft meat products. Here with us we have Dr. Hesam Haider, technical manager at Interop V Lab. with over 15 years of experience in automation, manufacturing, health system, energy, and robotics. His talk will focus on bridging the skill gap and preparing the workforce for the integration of flexible robots and AI. Dr. Hayden, please go ahead.
Thank you, Martha. Can you hear me?
Yes.
Excellent. And the screen I'm trying to share.
We can see it. Yes.
Excellent.
Great.
Thank you very much, Martha, Linda, Lisa, and Lynn for the work that put together so this webinar is taking place. For Agile Hand, as you mentioned, it has three main suites. So it's for sensing and packaging of and handling as well deformable products. With this topic today, I will be dealing with the more specific issue that the Agile Hand project deal with, which is the human side or the human-centric issue with the integrating robot and AI in the workplace for automating some complex tasks. So I'll just brief you with an overview of the background of some trends on the industry, as well as the importance of evaluating the assessments of the competence and skills of the workers who work on this particular sectors, and as the projects deal with the multiple sectors, especially for agriculture and fish and meat, since they are parts of the deformable products. Then I'll quickly highlight some of the challenges and risks, and we'll conclude with some closing remarks. To highlight, this is a part of one of the work packages that deal with the human aspects of social science, the projects, and this work not only handled by Interoperability, but by mostly three partners of the projects, which is Factor Social and University Politecnica della Marche. When it comes to deformable objects manipulation, it's a complex issue, whereas the specificity of the product itself is difficult to characterize, since it has a high dimension for the configuration of the space between points within the products. So it's not an easy situation. We could characterize the products, even though we could assume make some assumption for the rigidity of the products on robotics overall. But whenever we imply impose some force, the dimensions of the products will be deformed. This is on the technical level of the issues that the project is dealing with, but with the specific of one of the work package, we deal with the some specific application on the social aspects. So there's this integration of flexible robot and as well as the AI has or will transform the workforce. So this automation will shift the job roles or change some of the competence needed or the skills that required to achieve certain tasks. But also there are some other concerns which is related to safety and security. And safety, it's not just safety for physical distance or safety for hazardous environment, but the digital safety and security, which it's about cyber security, data privacy, etc. some of the trends on the industry, it is, as I said, the integration of the flexible robot. So these robots are used to enhance the productivity, but also to be placed on a hostile environment or more dangerous environments, so that to keep the human operators a bit distance of such environments. But again, we come back to the essential of the specific focus of the work done here is the social impact. So we try to see what could be the double facets of this integration, which could be positive, where the productivity is increased, the robot is integrated in hazardous or the hostile environments. So, but there's a negative concern, which is job displacement, as well as the ethical dilemmas. In the European ecosystem landscape, the EU has some certain policies and some certain strategies or the initiatives that put in place, specifically deal with the integration of robotics and AI, such as the ethics guidelines for trustworthy AI Act, as well as the GDPR policy. And one of these initiatives that gets less mentioned, it is the Digital Education Action Plan, which promotes the adaptability of the workforce. So they could be up to date on the what exists on the what emerged on the market, and it's more focused on to be more human-centric, ethical, and transparent. There are some consequences of the rapid change of the work environment, which is the job displacement as we move towards more automated tasks performed by machines or robot. Some manual work or some manual operators will be displaced, and some workers might displace the competence they have already gained over the years. And then when they displace to other, maybe some departments or sections, they might have skills gaps. And then there are some consequences of psychologies, whether it is on the stress on losing jobs, or maybe on the continuous digital monitoring, since there could be some systems on place to monitor how some tasks are performed. What we did in specific work within this aspect, which is the social application, we did the analysis in two use case, which is the two pilots of the project, which is Santa Ursula and Rodoma. And they are not very big companies, but they represent what could be the wide range of what exists on the ecosystem landscape. So we have one Italian cooperative which processes small fruits, and then the family business which specializes in the frozen fish. For the data collection, we try to put in place some method triangulation, which we use multiple methods. One is the semi-structured interviews, which has diverse of the sources themselves, so it's staff, managers, and HR, and of course safety and security, and then questionnaires which was autonomous sent to the employees as well as the head of departments. One of the main things that came back is the need for skills assessments, and then what's needs for the skills assessment is first to identify the gap between the current and what is required. So you could analyze what are the weaks or the strength of the existing competence of the workforce in place to ensure these competencies align with the organization goals or what is existed on the challenging market. And then there's a need for regular review as there's a rapid change in technology. So to keep employees up to date of the competence in the market, but also to prevent so that their skills to be less used or obsolescence, and then to of course to comply with the I would say the industry standards. And then of course not to just focus on the job specific technical expertise, but expand this to other soft skills which could be useful for more collaborative environments, as more technical platforms or tools are used. So the collaborations needs direct communication, open communication team work, as well as the problem solving techniques. What are the necessary skills for this for the changing rules? Since we are integrating a couple of robots on the shop floors or the environment of these companies, a continuous I would say oversees the digital competencies, so to improve the proficiency of the workers on using, as I said, digital tools, softwares, online platforms, and other digital resources. So the workers or the users are up to date, and then increase their awareness towards cybersecurity issues. So not to just expose the companies when they are using these digital tools. Then the ethical dilemma, where it is important to enforce the data privacy or the data security, respect the intellectual properties and other ethical implication, as it's pointed out by the several EU policies and strategies. Then enhance the adaptability and flexibility of the workforce. So embracing new technologies, I would say willingness to learn and continuous improvements. And then of course collaboration capabilities, where work could be effectively and efficiently delivered with more digital channels. Then, of course, not to forget the safety awareness, where some safety protocols to be put in place. Again, highlighting the digital threats and cybersecurity, as well as some other soft skills which involves the problem solving and critical thinkings, and this is involved some analytical and data visualization through using some dashboard, which is some of the digital tools that you use used on in these companies, and use more data-based evidence decision making. So this is what's firstly on the skills to be acquired, but now second point is the safety concerns, and it's highlighted by Bradley curve. There are 4 stages of the safety culture stages of corporates or companies, and reactive. The first one is reactive, and this is where the I would say the injuries or the less safety rate is high. So there's misperceptions or individualism analysis of the risk, which could lead to some dangerous situation. Then dependent, where the communication is a little bit passive, where the employees just follow orders or use protocols that just communicated by the management without their involvement within these protocols. But it is less, the injury rate is less than the reactive. However, it's still a bit of medium risk. Then independent, which is more focusing on prevention, and it has a good active communication between the management and the employees. And then the best one, where the most of the companies aim at to achieve, is the interdependent, where is the dynamic of the teams, whether it is safety teams, operator teams, management teams, work on highly dynamic environment, and the perception of risk and prevention is high. Then for the OSH consideration, there are some certain aspects that we need to consider once we evolve to think of adapting the workforce so that they comply with the industry standards and regulations. We have to perform regular assessment to identify the gap of knowledge on safety, etc. And then the management should have a big, I would say, commitment on engaging employees, as well as encouraging employees, putting in place an open communication method and direct method to communicate the risk and the safety concerns. Then for the safety behaviors, the management and employees should always promote the zero tolerance towards the dangerous situations, raise the accountability of negligence, etc. And then facilities and equipments and environments. There should be a regular check on the maintenance and availability of safety facilities and equipment, as well as continuous maybe feedback on the digital threats as well. For the teamwork, it's always a culture of the corporate, so there should be a mutual understanding for mutual responsibility to prevent dangerous situation or a hostile environment, and to put in place the required protocols and standards. And then, of course, for the reporting or the communication. There should be transparency on communicating and reporting safety incidents and accountability. Then for developing programs, there should be adaptive and dynamic programs which corresponds to the rapid changing on the technological advancement on the market or the industry. And then, of course, we put it in a final step, which is continuous monitoring on what is provided for the as tools and digital tools for the safety to be monitored non-stop and regularly. Some of the key elements that should be highlighted on the coming period or the future, though it might not be addressed within the left time of the projects. There should be some AI-driven safety tools and systems, and then analysis of psychological impacts on the integration of AI and flexible robot, and then of course developing adaptive training programs. And this is sum up my presentation. Thank you very much for your attention.
Thank you, Dr. Aider. We can now move to the next project. Okay, the third one is the Masterly project, which is developing flexible robotics solution to meet the demands of modern production lines. So they are combining modular grippers with advanced robotic technologies, all enhanced by AI-driven control and perception for autonomous operation. They are developing these technologies and they are validating them into 3 industrial use cases. They are working with elevator assembly, logistic and packaging for sportswear, and aeronautic production. With us today, we have Dr. Sarah Fletcher, the Principal Research Fellow at Cronsfield University, specializing in industrial psychology and human-robotic interaction. She leads the Industrial Psychology and Human Factor Group, focusing on trust, acceptance, shared awareness, and safety in manufacturing. A presentation of today will explore how to optimize worker acceptance and well-being in a human-robot production system. So, Dr. Fletcher, over to you. Yes.
Good afternoon, everybody. I'm just going to try and share my screen now. Okay, hold on, bear with me. Have I been given permission? It's telling me that I've not got permission.
Oh, all right. Great. We did some practice before, but yes, you should have it.
Okay, let me try again.
Yeah. If you cannot, I can share your screen, your slides. That's no problem.
Yeah, I did a couple of alterations, so I'd like to try and share them.
Okay.
Try one more time. No, it's just showing me that.
Yeah, we are seeing your screen, so
yeah. Okay, so maybe if I do it that way.
Yeah.
Okay. Okay, so you're seeing my screen now. So if I do that, you can see my screen. Yes.
Yes, we. So
okay.
yeah.
Is that working? Okay. Good afternoon, everyone. Sorry about that. I'm Sarah Fletcher from Cranfield University in the UK, and a horrible grey UK today. And I'll be presenting on behalf of the Masterly project.
Sorry. We see your screen, but we see the browser page.
You're not seeing my slides, no?
No.
Oh, okay.
Sorry, I thought they were.
Okay. Let's try one more time. It's gone so well, hasn't it, for everyone else?
No.
Try this. I think is that.
Okay, yes, we can see that.
Bang! Tried it. Sorry about that.
Don't worry.
Okay, so that should be working now.
Mm-hmm.
So the content of my presentation, I'll try and move on a bit more swiftly, is that I will give you an overview of Masterly. Thank you to Marta and Linda for the introductions and arrangements here, and they have introduced some of Masterly, but I'll give you another broader overview. I will also introduce some of the core human-centered work. I mean, it crosses across, right across the project, but I'll focus particularly on 3 work packages where Cranfield University are particularly involved in attending to the human-centered aspects, and then provide a summary at the end. Okay, so as with all of our lovely European projects, there are a great number of partners across various countries and organisations. And Cranfield are the only UK partner, which isn't unusual, but it's very multinational, as you can see, including Ukraine, quite a strong participation from Greece and Italy, and also including South Korea, so it's a little bit outside of Europe as well. Okay, so thinking about Masterly objectives, one of the key issues that we wanted to address, or 4 of the key issues, were gripper flexibility and the current problem or traditional problem that grippers are generally dedicated to specific applications and are not readily interchangeable. Another key target was the programming of robots that haven't been user-friendly in the past and required skilled personnel. We wanted to address the need to make those less of a specific skill, something that could be adapted more on the job, more flexibility. We wanted to address the lack of cognition for autonomy, the fact that robots were not able to automatically adjust their behaviour according to needs of surrounding environment and people without programming. We wanted to attend to a more seamless and fluid interaction and changeability, and to address software solutions which have been hardware specific traditionally. So here is a vision of from our proposal, our original vision of how a modern process would look. Sorry?
Sarah, sorry to interrupt. We are seeing the first slide.
Oh, no, really?
Yeah.
I'm not having much luck.
I thought it was an issue, but yeah, no, I think we are seeing the first slide.
Okay.
But we can see your mouse moving, so I think
I think it is the second screen. If you just move the slides to the other screen, it will show up.
Mm-hmm.
I'm not quite sure what you mean.
Maybe you can click the slide to the left side.
Or disconnect from the other screen, the easiest way.
Oh yeah, maybe you're seeing a screen that we are not seeing.
Yes, maybe.
Yeah. Okay. If you do that, it's working. Okay.
Ah, right. Okay. So you can see this one now where I've got the picture. Right. Mm-hmm. Okay. Gosh, I'm really showing myself up. Okay. So going on to this slide then, as you can see on the left-hand side at the top there, those are the issues that I was discussing, the limitations of traditional production lines that Masterly is attempting to address. And below that, you can see a set of objectives that we've targeted, which is to, I won't go into these in great detail because largely these are technology based, and the purpose of today is to focus on the social science. But obviously you can see objective 3 is to develop user-friendly interfaces for robotics machines, control and programming. But as I will explain as we go through, the human-centered or user-friendly approach crosses other aspects of the project more widely. So just to go through our use cases in Masterly, we have the Kleeman elevator control electrical cabinets assembly use case that you introduced, Marta, earlier on. So the current state is obviously a very highly manual operation involving quite small scale assembly, and the vision is to move to a more collaborative system which would reduce the need for manual application of manual tasks that are unskilled, repetitive, not particularly healthy, not very enjoyable for the human operator to perform, thereby enabling them to focus more on the more skilled and cognitively satisfactory tasks. And we have some KPIs that are beyond the ones that I've listed there. I'm focusing very much on this in this presentation on the human-centered aspects. So we're aiming for reduction of manual tasks via the implementation of robotics by around 50% improvement, productivity in terms of cycle time reduction of a 40%, which isn't necessarily a human-centered approach, but it relates to the other issues below that, which is to focus on psychological impact and increasing worker acceptance of the new systems by 15%. And the cycle time reduction is also a key driver of improved ergonomics by reducing task time and musculoskeletal risk. So reducing the amount of time that the operator is engaged in posturally or physically demanding strenuous activities that are not very conducive to well-being. Moving on to the decathlon sportswear logistics and packaging use case, we have the current state where manual operators walk through large areas of a warehouse and pick orders, individual orders for packaging and sending out to customers. And the Masterly vision is to automate this as far as possible. Again, reducing manual strain like the Kleeman case, and to focus on improving the human enjoyment of the task, allowing them to focus more on the quality control and skilled aspects of the task, and removing the physical manual handling strain. And again, we have a productivity and performance target of about 80% improvement by reducing the manual tasks using automation, in reducing cycle time reduction, increasing, in this case, worker satisfaction as well as acceptance, and by, again, the 15% reduced musculoskeletal risk target. And then finally, I do apologise. Oh no, that's right. So the Aeronova task, use case task, is currently a task that involves quite heavy manual handling, moving large components in aeronautics around, and our target is to implement a human-robot system, which actually is not as collaborative as the other two use cases. Because the aim here is to replace that heavy manual handling and the risk of injury and collision that it involves, focusing on allowing the human to conduct the smaller assembly tasks, the more cognitively skilled tasks, and take away that dangerous heavy lifting. And again, there you can see some human-centered KPIs, and the description of the improvements that we're trying to achieve there, very similar to the other ones. So moving on to what we are doing in terms of the human-centered analysis. In work package 1, it's worth mentioning we engaged in some user-centered requirements capture. And then in work package 4, we focus on user-centered design of interfaces. And for that, we have adopted a three-stage or three-spoke methodology. one aspect of the methodology is to really focus on understanding what the human currently does. We believe that it's very important to, before doing any design and implementation work, to understand what the tacit skills involved in operations are. We can look at standard operating procedures and work standards to understand what the system designers intended people to do, but we know that people don't tend to do stick to those very rigidly. In many cases, there's often deviations from standard operating procedures. For good reason. We know that operators tend to adapt things because they want to make it better, easier for them for personal reasons. Maybe it could be their physiology or their natural abilities, or it could be that they find a better way than was originally designed. So we want to understand that, and we use eye tracking for that, where we get operators to perform their tasks wearing the eye trackers, which gives us operators' own perspective of the task being executed. It gives us a good combined field of view, horizontal and vertical view. And we have these systems that involve, the eye tracker systems that involve accelerators, gyroscopes and magnetometers, I can't say it, which accurately track their eye gaze and compensate for head movement. So we get a very accurate video recording, but also a microphone recording the verbal communications, which gives us additional detail. Excuse me. This gives us some various outputs, including those examples that I've put there in the small pictures. Some heat maps, which show us how much people look at certain areas. So it shows us the intensity of where specific parts of the field of vision are concentrated on. That's important because it shows us what grabs people's attention, and therefore this could indicate, it could be explained by areas of the work naturally, but if we ignore that, we can also look at how that might infer that these are areas of problems and issues, for example, where they might need to really focus on something to get it right, or because there's some confusion. We also look at dwell times in that middle picture there. That's an example of where we can see how people have looked at things for a length of time. Again, that may indicate where there's a problem because there's extensive decision making needed, some confusion, etc. And we can also look at scan paths, which is the order, the sequence, if you like, in which different areas of a field of vision are looked at. And that indicates what gets people's attention first, or cues to action, what they then need to do next, and so forth. And these are really good indicators of the current manual task, how it's being performed. They tell us where those problem issues are, and that then can advise us on where we may need to design out problem areas, where a robot would actually be more beneficial because it could be designed to take away some of those problem areas, or where the actual manual process itself in the human-robot interaction needs to be redesigned. So this analysis shows us the areas of the task and environment that demand greater attention, decision-making, that are prone to error or difficulty, or those that are effective cues to aid awareness. And we find that eye tracking not only gives us that objective output, we can also use that recording for playback to the operators if we want them to tell us how they do things. And so because a lot of what they do is so based on tacit skills and non-technical skills, they're not always aware of that procedure. It's like we always use the example of driving your car to work. There's a lot of aspects of that journey that you wouldn't be able to tell us if we asked you to tell us about it, because it comes naturally. But if you recorded it, you would be able to then explain, well, this is the indicator for when I turned right. This is, you'd be able to then recall more about that, the decisions you made and the task process you undertook. Excuse me. So the second part of our work package for user-centered analysis was to conduct hierarchical task analysis, and that's based on the eye tracking videos. Hierarchical task analysis deconstructs manual processes into individual component steps at various depths of scrutiny that suit the analysis, and it helps us reveal deviations from standard operating procedures. It helps us identify those decision-making points. helps indicate the process change potentials, where there may be, again, we identify those problem areas and where we might need to design those out when we redesign a process to use a robot. We also use task decomposition, which is an extra layer. It extends the HTA by providing another layer of analysis that classifies steps into things like cues, decisions, actions. And so we can identify the steps that utilize tacit knowledge and skill. And that's important because tacit knowledge is often the part of a human operation that shouldn't be maybe transferred to robotics. It's that sort of skill and creativity that only a human can bring. And it helps us highlight error points and then identify remedial actions that we can integrate into the redesign of the process. This analysis shows us the specific steps of the task that are problematic, that helps us to engage in user-centered design and more effective function allocation. The third part of our user-centered analysis is the application of psychometrics. So we use psychometrics, as you all know, to capture current levels of psychological states, indicating potential areas of concern in the current processes. And also this provides us with this quantitative baseline data set against which we can measure impact in future assessments. So gathering a baseline of how people are responding to the original manual process means that later on when we implement our solutions, we can then measure again and we can assess the differences. And so we can hopefully, it's improvement, measure those impacts and assess whether we're achieving those KPI targets that I mentioned earlier. We use various psychometric tests. We tend to use reliable and valid assessment tools that are already available because they have proven validity and reliability levels. And so three key ones that are used in Masterly here are the physical discomfort scale, because we want to assess the difference in ergonomic, postural, physical differences between the as-is manual task and the to-be one after we've implemented solutions. We measure mental workload because we know that's very, very important to how people, how satisfactory a new system is. And we are not targeting blanket reduction in mental workload at all. We measure 6 dimensions of current mental workload using the NASA TLX, and we use that because we know there are optimal ranges of mental workload. We don't want to go for too little workload because we know that then is unsatisfactory, and we don't want to overload people. So we need to get that optimal range. And we also measure situation awareness, which we also know is very important for automated systems. People need to understand what's happening at any given time. So we want to ensure that we also achieve an optimal level of awareness in relation to task characteristics. And this analysis overall allows us to understand the physical and psychological impacts of the project solutions and quantify them. So those three together allow us to understand the user-centered design of interface, to improve it, to understand what needs to be allocated to a robot better. In work package 6, we are undertaking a methodology, we're defining a methodology to assess operator acceptance and psychological impact. We have our tried and tested methods, but we understand that these are often quite generic, and we want to apply them to the specific context of Masterly and then understand how they might be developed for industrial systems per se. So for that, we are undertaking some exploratory studies in the use cases, because this is the only way we can get a fundamental idea of how people envisage systems being changed. And when I say people, I mean the subject matter experts, the users themselves, the end users. They are our experts in these manual processes, so we want to utilise their input as much as possible. So we put the end users and operators into small groups in human-centred and ask them to undertake human-centred design activities, which is to co-design and redesign, if you like, solutions. We give them stickers and graphical activities. We show them videos and give them creative materials to use. There's some examples on the right hand side in those photographs there. Excuse me. We also use that opportunity for group discussions and brainstorming, using a semi-structured format which allows them to freely speak and generate their ideas. And using this method, this kind of free and flexible method, they can locate successful and problematic task environment characteristics. They tell us what works, what doesn't work, what they want to see, what they don't want to see. So that it gives us the as is current state viewpoint, but also what they envision for the future. It allows us to capture their attitudes and perceptions related to the acceptance of new technologies and processes. So we can also, at this opportunity, also give them some of those psychometric scales that I described in the last slide, so that we can also sort of get a gauge on how they feel about these their tasks in that way. And we can identify change management enablers and barriers, those things that they tell us that we know is going to optimize the integration of the new systems, and what are those things that might prevent them, so we can work on those. Excuse me. So the analysis provides us with qualitative data from real operators or end users that indicate the key human factors that we need to focus on in specific use cases, and as we do that, the key part of these exploratory participatory design workshops is it engages the workers. They are giving us their feedback on these new designs that are going to be implemented, and that means that they start engaging. They can see their feedback being implemented as the process goes along. That optimizes buy-in essentially and their acceptance of the new systems. We also engage in experimental studies, and we are now at the stage of just starting to begin these. And these are for targeted assessments of prototypes. We base them on the exploratory results, in that what we've learned in those participatory design workshops and focus group discussions beforehand help us to understand the issues that we need to focus on. But we also need to look at specific aspects of those objectives that I presented right at the start of the presentation, which is looking at the interface and communication modes, looking at different types of grippers, and also taking behavioural measures. So it's things like the task time, remember the cycle time that I mentioned, looking at errors, and looking at those that broad range of issues that we know we need to look at. In those experimental studies, we will measure physiological and psychological reactions in different conditions, so that we can triangulate these multiple methods. We include the eye tracking, as I've previously described, because we can use eye tracking in experimental conditions as well. We measure stress responses such as heart rate, skin conductance. Sorry, I've spelt that wrong there. We can measure neurological activity responses, so the frontal cortex blood flow measurements, which indicate stress and decision-making activity. We can analyze facial and emotional changes, and we can also use motion capture for physiological analysis as well, and we can feed that into CAD modelling as required. These various techniques we support with qualitative data collection as well in experimental conditions. We know we should never rely just on objective measures, because they tell us how much things change or are changing. They don't tell us why. So we always triangulate with qualitative assessment as well. So when we measure, for example, heart rate and skin conductance, and if we see deviations and variations, we will accompany that with questioning people, interviewing them, and asking them why things changed at those peaks and troughs and times as well, so that we understand not only the how much, but also the why. Okay. Moving on to work package 7, which is the final work package I'm going to talk about in terms of human-centered analysis. This concerns standardization, and it's about creating a roadmap towards human safety in standardization. And as you can see from the clip from our general our general agreement there, we're aiming to focus on three main aspects, which is understanding the open or vague areas or missing norms. So what that means is we want to understand what guidance we need that is not in current standards, because current standards regarding robotics are there's very scarce attention to any psychological or emotional impact on users. It tends to focus very much on the technology and the engineering side of the systems, which is has been absolutely apt. But with increasing human-robot collaboration and human interaction between people and robots, we know that that needs to change. So we want to do a review of what guidance is currently not, that we need for these new systems that's currently not in standards. And we're going to do that by undertaking assessments with technical partners, consulting and surveying our partners and other experts to map our requirements to existing standards, to understand exactly what we need in new systems that isn't currently covered. The second part of that is updating existing standards. Well, we can't do that. Hello?
Oh, sorry. We are running a bit out of time.
I'm going to finish up very quickly. Okay, I'll speed up my chat.
Sorry.
Okay.
Sorry.
Okay, so we'll look at which standards need to be addressed, and we'll do that with identification through existing contacts. We can't automatically update existing standards by any means, but we can understand which standards need to be addressed and consider the guidance needed. And also we need to demonstrate our compliance with the existing standards and understand those gaps. And we'll do that roadmap through I'm involved in existing standardization through those roles on the right hand side there. And I think the interesting thing there is I'm perhaps the most important thing is my liaison between TC299, which is robotics, and TC159, which is ergonomics. Moving on very quickly, sorry, this is due to the technical issues at the start, I imagine. I won't talk about the first two there, 10218 and 22183, which is work that's either just been released or currently under development, because again, those are very technical topics and technical standards. But I will focus on the bottom two, which is the CWA, which is one that I authored in a few years ago, which basically sets out standardization of methodology for developing psychometric assessments relative to industrial automation contexts. And we are going to be extending that in Masterly. And also to mention the BS 8611, which is a British standard, but it was the world's first robot ethics standard. And we revised that in 2023. And that provides a framework for ethical risk assessment, and in Masterly it will form the basis of a new tool for design and integration. So very quickly summarising, I won't go through all of this, but as you can see, there's a range of outputs that we're aiming for there, and achievements that we're aiming for in the project. So thank you very much, and sorry if I've overlapped. Thank you.
Thank you, Sarah. Don't worry. Okay, so now, last but not least, we have the HARTU project. So we have nearly done. So the HARTU project is an industry-driven project aimed at achieving flexible and efficient manufacturing through AI-enhanced gripping, assembly, and placement technology. By developing adaptive grippers and learning system, HARTU enables production lines to handle a wide range of products in terms of shapes, materials, and size, enhancing flexibility, reconfigurability, and the overall efficiency of the production line. HARTU is being tested in 5 real-world industrial use cases across different sectors. We are working with the automotive, consumer goods and tools, foods and logistics sectors, spanning through Europe, Turkey, and Taiwan. With us today, we have Giovanni Pignoni, a researcher and designer from Deep Blue, specializing in human-computer interaction and human factors. His expertise lies in cognitive workload assessment using eye tracking and its real-world limitation. Today, he will introduce us to the human-AI team interaction model and how it advances human-AI collaboration. Please, Giovanni, the floor is yours.
Okay, so hopefully you are seeing my slides.
Yes.
Okay, so, well, let's start with just a short overview of what I will present today. So we'll start by talking about what we intend when we talk about human AI teaming in the manufacturing field. Then I will show you our human AI teaming interaction model. I will go through the various blocks that compose it, and then I will give you an overview on how we are using and plan to use the model in various use cases. So let's start by the beginning. The beginning is that there is quite an interest in introducing advanced systems that include artificial intelligence in manufacturing. And so teaming has emerged as an area of study because this sort of system creates, or rather enable, interaction that are a bit more akin to interacting with other human worker rather than the old paradigm of a worker interacting with a tool. So when we talk about teams in manufacturing, we talk about teams that involve one or more members. Some are human operators and some are AI agents. And these AI agents have a level of autonomy sufficient to make them recognizable by the human operators as a distinct entities that can have a role and that can have responsibilities within a task. So again, something that is more similar to operating with another worker rather than having control over a tool. Now, the level of autonomy is something that can vary a lot. So we start from something that has very low autonomy as a personal assistant that is only doing things if we are asking them, and perhaps is only giving a suggestion, to autonomous agents that are able to take decision and adapt how they operate independently with no human involvement. So on this spectrum, we still talk about human AI teaming. Then, so from this, we decided that we had to develop a human AI teaming interaction model. And the reasons to do so is that we felt the need to develop a tool that would give us a common language, both internally in Deep Blue, but also when we are talking with other stakeholders in a project. A common language that would allow us to describe teaming and that would allow us to also document all the various bits of information that we collect as we approach a use case that we think, based on what the literature is telling us, but also on our years of experience, that can affect teaming. So all the important bits that are sort of contextual to the introduction of human AI teaming that can affect it we try to capture all of these in the model. And once we have all these things, the model allows us to have an overview of how things are interacting with each other. And so if we have an issue, and by issue I mean, for example, a lack of trust in the AI system, we know which variables we can go and affect to try to fix this. Finally, at the end of the project, we might want to do validation of a system, and this model is also helping us to find out which things are most importantly in that use case to be validated, and also how we can validate them. And I'll go again through all of these things as I explain the model. So this is the model itself, and don't worry if it's too small to read. I'm going to go through each block one by one. But the overview is that we have from the outside inward, we have two blocks that are the environment and the task. These are the context in which the team is supposed to operate. So where they are operating and what they are supposed to do. And they are part of the model because we think that the team can be a unit that is asked to do multiple tasks and can operate in multiple environments, but still it's affected by these two blocks. So it is part of the model, but it's somewhat separate. In the middle, we have everything that make up the team. So the two protagonists, the agent and the operator, and what makes them interact, the mediator. So let's look a little bit deeper at each block. First, I would start from the environment. The environment, as the name suggests, is about collecting information on where the team will be deployed. But this is not only physical information, it's not only about the ergonomics and location in a factory, it's about also the cultural organization of the company, for example, internal policies, but also the ethical and legal framework we might have to work within. And as you can imagine, this is quite important, especially now that there are new regulations, the AI Act, that will increasingly regulate how we introduce AI system. So we need to have an overview of that. And finally, we also need to have an overview of what is what are the economical requirements and the performance requirements that might come from the stakeholders. And this is something quite critical because every intervention, like the introduction of an AI system, will have a very real cost. So from the beginning, we want to start to have an idea of what the various stakeholders expect to get out of this intervention. And this is quite important because it's what we can refer to at the end during the validation to see, did we create a system that actually satisfies what we were set out to do? And if not, well, then we can backtrack and find out what went wrong. Then on the bottom, we have the task. And again, this can start by just describing what the team is supposed to accomplish, breaking it down in subtasks and goals, but also it should capture a bit more information about the demands that the task will have on the operator and the AI system. So are we talking about physical demand as lifting heavy objects, or mental demand of solving problems, making decisions, and also how the task is affecting the interaction between the AI system and the operator. That is there an overlap between them? Do they need to cooperate in certain parts of the task and work independently in others? This is all things that we want to capture in the task. Sorry, went to the wrong one. Okay, now we go to the core of the model. This is the team in itself, and the team is sort of split in two. We have again the two protagonists. On one side, the agent that is further split in the software part and the embodiment part. By embodiment, we mean all of those things that pertain to robotics and sensory systems, while the software part are more about perhaps the AI model that is running behind the scenes. On the other side, we have the operator, and in the middle, what connects them. Now here we have, if we start from the agent, we have some variables that are a technical description of what the agent is. We are trying to capture, okay, is it an LLM that powers a personal assistant, or is it, say, a computer vision algorithm that does sorting of objects? That should be described here. But on a more abstract level, we also want to know what kind of outputs we get from the agent. For example, the explainability that we are getting out. And also, is it trainable? Is it going to learn and be taught by the operator? And also, here we have the opportunity in the design stage to start to look at concept as the mental model of the agent. How do we want the agent to see the world and see the system that is put in? Or also, how do we want the agent to conceptualize the operator? How will the operator respond to inputs, and what motivates the operator? And all these things that are things that will sort of define how the agent reacts to the world and the operator, and that we should discuss in the design phase of a project. On the other side, we have the operator, and the operator is defined with, let's say, very common human factors terms. So we are trying to have a profile of who will engage with the agent. And this can be both in terms of capturing who are the workers that are already in a company that will become teammates, but also perhaps seeing what these workers need to become the optimal operator. So perhaps we will have to do training and reskilling to make them fit better in this framework. So this should be captured in the operator side. In the middle, we have the mediator. And the mediator is everything that allows the agent and the operator to interact. So we start from sort of a simple level of UI and UX, how the interface is made, how do they communicate, but also we have a layer that should describe how perhaps how procedure affect their communication. How do we solve conflicts? If the agent is proposing a solution and the operator is proposing a different solution, how do we solve this? This is defined as a procedure, and this will then sort of create a hierarchy and an authority structure of the team. So when we have these three things interacting, we arrive to the team and teaming side of the thing. And this is sort of divided in two, and you could look at it as two sides of the same medal, because the team for us is an expression or a description of the emerging interaction between the agent and the operator. So we start to talk about concepts such as shared mental model, shared situational awareness, and shared goals. And these are things that emerge from the interaction of these two protagonists, but also there are things that we can in part design and say, okay, we think that in order to better engage in teaming, we need to have a certain type of shared mental model. But on the other side, we also will want later in the validation stage, we will want to see if what we desire, what we designed, is actually what is happening in real life. So then we start to talk about teaming as all the metrics that can let us measure teaming, so a manifestation of the teaming that we can actually look at, that we will consider in the validation stage. And I will touch upon this a bit later, but basically there should be a connection between concepts such as shared mental model that are not necessarily directly measurable and other things that are directly measurable, but that will let us infer whether shared mental model is good or bad. So now I can move on to the overview of how we are planning and or are actually applying the model in various use cases. And the idea is that, we would, if possible, start early in a project to apply the model. And we would start at the beginning by collecting context and requirement information. So in this stage, basically the teaming model is a container of information, and it guides us in collecting information. So it helps us while we are conducting workshop and interviews with stakeholders to ask the right question and make sure that we have a complete overview of what the teaming is supposed to be, at least for what is actually defined at such an early stage, and what are the requirements that the stakeholders have. And also the main output at this stage is that we are able to identify if there are things that haven't been discussed by the other stakeholders, and then as mediators we can go in and ask the right question and elicit certain reflection from them. For example, if you take an example, one of HARTU's use cases, this is from TOFAS, we have a task where a robot and an operator are supposed to pick and place parts from a container. And so at the beginning of a project, we would go in and talk with the partner at TOFAS or also the technical partner that will perhaps implement the solution, and start to gather information of all the information about what the task is supposed to be. Perhaps document the as-is scenario, how the task is being now carried out by the operator on his own, and how the task is expected to be at the end of the project, the to-be scenario. And in this case, perhaps we have an idea that the task is still going to involve an operator. The robot should do most of the work, but an operator will still be there in some capacity. So we know there is a form of teaming, and we can go on with this information and refer to it as we go forward in the project. So after we have sort of solid basis of gathering all this information from the other stakeholders, perhaps we go through the design stage of a project. And in this stage, the model helps us as a repository of information, because we refer to what we collected earlier, but also it helps us mediating the design. And I think a good example of the mediating process is the work that we have done with the definition of roles. The definition of roles starts from the need of being able to discuss in plain words with the other stakeholders and define what do we expect the two team members to do. And so we have created a narrative model of teaming, a narrative model of the roles that basically creates, or we try to map at least a comprehensive list of roles that the AI agent and the operator could have in a team, and allows us to do a discussion. For example, here again is for the example from TOFAS of what combinations could work. For example, here we had among the desired combination, we had an independent AI, so an AI that is doing most of the work, paired with a passive user, so a user that is almost not involved, or a collaborative AI that is doing a good part of the work, but then has to perhaps ask for help to an helper user when there is an unforeseen situation. So we had this discussion in a workshop with our partner TOFAS, and we tried to find out, okay, why are these the desired combination, and why are these the sort of the optimal combination that we might have. And also, if you see here in the list of roles that we propose, we also have a few that are definitely not desirable, such as a faulty AI and a clumsy user. And these are actually here to have a discussion on what happens when we have human error in our system. Is the system resilient to human error, or whether we have an AI that malfunctions? Is the system resilient to malfunctions of the AI? So we can also have a discussion about those cases. So again, this is a narrative approach to the definition of roles. It's not it is not producing requirements on the development of an AI system directly. It's more about having a discussion early on with the other stakeholders and imagine how the teaming can play out. And I think this is quite important, because as it has come up already earlier today, there is often a lack of discussion on what the operator will do. We end up having perhaps underutilized workers where the technology is sort of taking the first the spotlight, but this can create a situation where you have an operator that is not really engaged in what he is doing, because we are only applying leftover allocation. If we early on have a discussion and we imagine how the operator will interact with the AI, then it's possible to have a meaningful relation between the two, and actually have a teaming that is positive and sustainable. So after the design phase and after basically we have updated our model with all the things that we think we want, we have the implementation phase. And in the implementation phase, usually the technical partner will step in and translate this high-level teaming description into description of what is actually going to be implemented. So again, the model here is mostly being updated and going from a description of the design to a description of what will be implemented. And then, of course, it's up to us to compare the two and see if there are discrepancies. And finally, we have the final step, that is validation. Validation is about evaluating something that is being implemented. Of course, this can be at many stages. It could be a prototype, as it could be something that is actually being deployed. Depends on the project. But the main point is referring to what we have designed and see if the implementation is actually reflecting that. And the main use of the model here is, first of all, as a reference, because hopefully, if we have gone through the entire process, we have very clear requirements coming from the first two steps, but also it should give us an idea of which teaming variables are most important in a certain scenario. So, for example, again, if we believe that shared mental model, a certain shared mental model is of particular importance, and this is quite often the case because shared mental model is one of the variables that really enable teaming with multiple team members, then we might want to organize a validation plan that includes some things that can make us infer, that lets us infer if the shared mental model is structured correctly. But since shared mental model is not something that can be measured directly, then we look at things like adaptability, whether the team is able to adapt to different situations quickly on the fly, or their communication. And the model is also suggesting this connection. And so it's used to translate high-level concept into concept that can, or actually not concept, but variables that can be measured in the field. And finally, on the validation, I would like to add that we are not only looking at human factors variables, so we're not only talking about mental models and workloads and things like that, but the validation should include also requirements that relates to KPIs, productivity, safety, legality, and ethics. And all these things are hopefully captured in the task description and the environment description so that we have a reference to compare our results against. I think that's about it. Maybe a bit over time, but just to summarize, we think that human AI teaming interaction model can be quite beneficial to many of our projects because it allows us to have common understanding with all the stakeholders and discuss teaming early on in simple words, find issue early, and also have an idea of how we can modify our system to affect teaming and correct this issue. It also should support good discussion that make us design teaming that is flourishing. So create meaningful roles, create meaningful task allocation, and also it should help us validate and plan should help us do validation planning and also iterative design so that we can improve our design over and over. And well, I think that's all. So if you have questions, hopefully there is a bit of time for this.
Yes. Thank you, Giovanni. Thank you to all the speakers for their presentation and for being with us today. And thank you all for being with us, our audience. So now we love to hear your questions, your curiosity, if you have any. If you want, you can type in the chat your questions, or if you are brave enough, you can raise your hand and you can speak directly with our speakers. So yeah, with Linda and Elisa, we are trying to collect your answer. But as I can see, there's already 2 answers in the chat, one for SMARTHANDLE and one for HARTU. I think we can start with SMARTHANDLE, so Giovanni has time to recover from the speech. So yeah, for SMARTHANDLE, we have Christopher, who has mentioned early that human-robot collaboration is based on trust. How did you assess or measure trust?
Okay, we can think about objective measurements of trust in the same way that we can measure between human and human. We can think about indirect ways to measure the trust between human and robot. For example, using some kind of sensor located on the skin of the operator, trying to measure the sweat of the skin, or tracking the eyes of the human, or tracking the whole body movement around the robot, or measure the breathing frequency of the human, and trying to infer how comfortable the human is when he's working together with a robot. This is one way to measure in a indirect way, and also we can, of course, do interviews of how the operator feels after having shared the workspace with a robot and checking their feelings. I think it could be a way to measure the trust.
Thanks.
Okay.
Welcome.
So, Christopher, if you want, you can give your answer, your question to Giovanni yourself if you want to, or I can read it. I don't know. It's okay.
Right, sure. I was listening to your presentation. So as it says, could you give an example of a real world task that you expect your AI agent to be engaged with collaboratively with a human?
So do you, because I mean, the human AI teaming interaction model, it's not an AI agent in itself. This is more of a framework for us to design systems where an AI agent is involved in. But if you are asking about the example by TOFAS, then perhaps I'm not the best person to ask this, because this is being developed by TOFAS, not by Deep Blue. So what in Deep Blue we are developing is a model that is a descriptive model. So it's not, it's more, at least for now, mostly a way to organize information that describe the human AI teaming and all the factors that go into it. And eventually it will should also give us some information to at least predict how some things interact with each other. But there isn't, it's not an AI model. Regarding the TOFAS example, that's one of the use cases within the HARTU project. And that particular use case is about sorting object out of a container. But yeah, I think if you want to know more about that, perhaps one of my colleagues is more suited to answer, because I haven't worked directly with that use case myself.
No, that's fine. Thank you.
Yes. So next question is for Masterly from Hannah. Could you share some more information about the experimental procedure? Do you use the prototypes that have been developed in Masterly?
Hi, thank you for your question, Anna. So our experimental work has been delayed slightly because the prototypes have been delayed slightly, which is typical, isn't it, in research? But the experimental procedures will be human participant studies to test, yes, prototypes from the cases and that have been developed in Masterly. So that will involve, for example, I think Chris, who's just been talking, is actually one of my team. So he's just been out to Greece, to the teaching factory there, to test some prototypes out there, and there will be more of that kind of experimentation. If it's possible to do experimentation in our own lab using mock-ups that are based on the prototypes being developed by our technical partners across Europe, then we can do that too. So, for example, if there's a virtual reality or AR system that we can use in one of our that we can replicate or transfer to one of our AR devices, then we'll be able to test human participants where we are. So that's kind of, it's very flexible. We will conduct our experimental work based on what's needed, and as well as what we can do without traveling, and so it's a mix between the two. Does that answer your question?
Yes, definitely. Thank you very much. Oh yes, we have a hand raised. So Apostolis, please go ahead.
Yes, hello. This is Apostolis, coordinator of Masterly. First of all, before getting to the question, just a big thank you to the organizers. Quite interesting workshop or webinar, and thanks to all the participants. I think we had the chance to hear a lot about this interesting topic related to SSH in robotics. My question is perhaps towards all of the participants. It's mostly related on how we can assess the trust, but also other SSH aspects in the different cases of robotic applications. Either this is a simple interaction of the operator with a robot, like for example, sending voice commands, or in a different case of cooperation with a robot in the shared workspace, or even difficult in real collaboration with a robot like manual guidance. So is there a difference on assessing these factors, or we should consider them all under a common agenda, let's say?
Who would you like to answer?
I could start briefly.
Please go.
Thank you very much. It's an important question, and it's a complex question as well. Assessing the human factor within such type of projects is always influenced by how biased are those we are conducting the study with. So if we are collecting, let's say, a survey, or we conducting an interview, there might be a bias on the answers that we will be receiving from the operators, or the managers, or the shop floor. So this answer will, just subconsciously, they think of what could be the sequence or consequences of the integration of such tools. So, for example, we always talk about losing jobs, or the stress of job displacement. So the answers of operators will be in a direction where they try to protect their jobs, or insinuate the less needs of, I would say, training programs, or the settings of integrating these tools. So the best scenarios, I wouldn't say it will eliminate everything, but it is to do a cross evaluation. So to collect the interviews, to collect the surveys, and to conduct a focus group, and then to verify the collected answers based on the answers with those who provided this based on focus groups. So that's these answers are more close to the, I would say, the appropriate answer.
Thank you very much.
Okay. I can add just a thing, because I think there is, if we want to look at the side of, say, of more observable measures, because of course what Hesam has proposed is perhaps the subjective side, but I think there is also a chance to look at the behavior of the operators and use that as an indicator of trust. This of course depends on the system, but there are things that can be used as an indicator of trust. A simple one that I could think of is just look at how much they rely on a system, whether if they have an option to avoid using it, that could be already an indicator of trust. So it all depends on how the system is of course put in place. But if they have an option to override the system, you might see if they have a bias. Trust can also be, well, it can be seen adoption rate, it can be seen if you have an experiment, you could also feed, let's say, false data or incorrect recommendation to your operator and see if they anyway rely blindly on what is suggested to them. So there are, I think, many ways, just as a behavioral measure, to look and assess if there is trust, and also if there is an abuse of trust, if the operator is not, say, double checking inputs from a system, and validate if the relation between the two is healthy.
So I take the floor again, Marta, and take the chance to thank everybody. We're running a bit late with respect to the agenda, so I'm really sorry, because I think we could also have more questions and topics to, share the respective positions. So in these terms, I would probably suggest all the attendees to this workshop to just get in contact if you have further questions, or even if you want to share your experience. Maybe you are involved in projects that apply SSH to their activities, or you would like to enter this type of topics, or you are, the other side of the SSH, so more the engineering and development part, and you would like to further discuss with us how we could truly design and operatively validate together the impact of the introduction of robotics into manufacturing settings, considering the, let's say, the impact on human well-being, and considering also the impact on the workforce, let's say, profiles. Also, I mean, while speaking and while listening to all the presentations, I was thinking that maybe we can, since the 4 projects will be closing by the end of this year, maybe we can join forces for, I don't know, organizing something more together, even for, producing some small, let's say, texts describing our experiences with SSH. And thanks, Jawad. And also, put together the expertise and the best practices that we have so far started sharing. So just let's keep in touch, both with the sister projects, of course, but this is, let's say, easier, but also with the attendees, especially if you have something you would like to share with us. So we will be happy to somehow promote also the building of a small community around the idea of social sciences and humanities, and application of social sciences and humanities to projects in Cluster 4, specifically even in the next topics, of course, which are due to be submitted by September this year. So thank you again, and have a nice end of the day.